In this video, we're going to go over graphing square and cubed root functions in detail. So first, let's go over the parent functions again. You saw these in graph translation theorem. Okay, so the parent of the square root function is just the square root of x. So the domain of the square root of x is x has to be greater than or equal to 0, and the range is that the output has to be greater than or equal to 0. Now, the domain starts when x is 0, so 0, 0 we can think of as its starting point. And then if we just made a table of values, I just plugged in x values that would make the outputs integer values, so I didn't have to use a calculator here. And notice I just have a bit more detail in my square root function in the graph here. Okay, but this is the basic shape of the square root. Okay, cubed root of x, you could plug in all real numbers because you could take the cubed root of negative numbers. And the range is all real numbers. The parent has a critical value of 0, 0. That's where we're seeing that shape of that turning happening. And here's just a few more points so that we get more of an accurate depiction of what the graph of the parent looks like. So remember, if I have the cubed root of x, if I plug in, if it's just the cubed root of x, if I plug in a positive number, I'm going to output a positive number. If I plug in a negative number, I'm going to output a negative number. If I plug in 0, I'm going to output 0. Now, all we're going to do is we're going to graph square roots and cubed roots, except we're just going to make sure we show them in more detail so we have detail so that we have more accurate depiction of what the graph looks like. So when you are graphing square roots and cubed roots, okay, you need to make sure that you have 5 points in the table of values. Okay? And one of the points must be the critical value. So if you notice, critical value is in the middle of the table for the cubed root because this is an important point to have. If you have 5 points that are just on this side of this cubed root, you would not be able to make it accurate. Okay, that's why you need to have this point, okay, and then 2 points that would fall to the right and 2 points that would fall to the left of the critical value. Now, critical value for a square root is really the starting point, okay, because there are no points that fall to the left of that value. Okay, so starting point and then a few points that are within the domain. And then just make sure you state the domain and the range. Okay, so let's get started. And you can keep a calculator on hand. So we're going to graph each function. So number 1, make sure we state the domain and the range. We'll do f of x equals 3/4 times the square root of 2x minus 1 minus 3. Okay, so first take a look. What type of function is it? It's a square root function, okay? So what we know is that there will be a starting point. Now, the parent starting point was what makes this 0, okay? So for the starting point of the parent, it was 0. But now there's changes happening. So what makes 2x minus 1 0? Well, when x is 1/2. Okay, so for the starting point, the x coordinate is going to be 1/2. And then if we plug in 1/2, okay, 1/2 makes this 0. Square root of 0 is 0, times by 3/4 is 0, minus 3. So the starting point is 1/2, comma, negative 3. So that's going to be our first point in the table. Now we just need to plug in values so that we get an accurate depiction of what this graph looks like. So I'm going to plug in, now think about it. Am I allowed to plug in numbers that are greater than 1/2 or less than 1/2? Well, that's all based on the domain, right? So my domain, if it's a square root, okay, if it's a square root, a 4th root, a 6th root, an even root, that can never be negative, okay? If it can never be negative, that means that it can be greater than or equal to 0. Saying it can't be negative means it can be greater than or equal to 0. So that's an interval over which we now have to figure this out. Okay, if I add 1 to both sides, I get 2x is greater than or equal to 1. So I get x is greater than or equal to 1/2. So think about the domain before you start plugging in points. The domain here is that x has to be greater than or equal to 1/2. So as long as I got to pick 4 more points that I just have to make sure are greater than 1/2. So I could plug in 1, okay, I could plug in 2, I could plug in 3, and I could plug in 4. And now, okay, the only thing that I want to be exact is the starting point, okay, and the critical value. So as long as the starting point is exact, everything else in the table you can round. So I'm going to plug in 1, okay, make sure you just, when you're putting your calculator, you've got 3 divided by 4, and then when you hit this, it opens the parenthesis. You have to do 2 times 1 minus 1, make sure you close the parenthesis, and then the minus 3 goes after you close the parenthesis after the radical. Okay, so I'm just going to use my calculator and figure this out. So 3/4 times the square root of 2 times 1 minus 1, and then outside of that, minus 3, and you get negative 2.25. Then plug in 2. Okay, we plug in 2 into our calculator, and we get negative, and we get, okay, it's not a pretty, okay? So just round to 3 decimal places. That's going to be 0.701. Now, plug in 3. We get negative 1.323. Now, plug in 4. We get negative 1.016. Okay, so this is what we have to graph. So 1/2 negative 3, 1 negative 2.25, 2 negative 1.7, 3 negative 1.3, and 4 negative 1.06. This is the starting point, so we start here and then go towards. And so let's look at our range. From our starting point, did our y's get larger or smaller? They got larger, so the range is y is greater than or equal to negative 3. There's a way you can figure out right away whether or not your range is greater than or equal to this value or less than or equal to this value. Is the a value positive or negative? The a value is positive, which means whatever this radical evaluates to be, which the radical can evaluate to be less than 0, we're multiplying it by a positive number. So it's going to be a positive number minus 3, which means it can't be anything below 3. If this was negative, a negative minus 3, it would be everything below 3. Okay, so that's it for number 1. Number 2. F of x equals negative 0.3 times the square root of 1 minus 3x plus 4. So the first thing is, this is a square root, so I am concerned with finding the starting point here. Okay, so what makes 1 minus 3x equals 0? That's going to be the x-coordinate of my starting point, because that's going to be the first value that's plugged in. The parent, remember, x was 0 because it gave you that unique output of 0. So we solve this, we get negative 3x equals negative 1. We get x equals 1/3. Now, I do not want you rounding that number 1/3, because if you round that to be 0.3, okay, if you were to plug it in, that technically doesn't give you 0, and that was that unique value you translated from the parent. The only value that actually gives you that is 1/3, so do not round the starting point. Okay, you can round any point in your table, but not this piece of information. So now, if I plug in 1/3, that makes this 0, times by 0 plus 4, makes it plus 4. Okay, now, in our table, okay, it's going to start when x is 1/3 and y is 4. But we don't know whether we should be plugging in values that are greater than 1/3 or less than 1/3. So right now is when we should be getting our domain. So our domain, we need to make sure that 1 minus 3x stays greater than or equal to 0. Otherwise, we're going to end up with an output that's with the value under the radical that's negative. So we have to solve this inequality, okay? Take away 1 on both sides. We get negative 3x is greater than or equal to negative 1. Divide by negative 3. Whoa, what's going to happen? We just divided by a negative. The symbol's going to flip. So our domain is actually x is less than or equal to 1/3. So my inputs all have to be less than 1/3. So let's look at what in this square root function made this interval flip from being greater than to less than. It's the fact that x has a negative in front of it. This means you're going to take all of the opposite values of x. So in this one, x was greater, but if you're saying you're taking the opposite x values, they're flipping to the left. Okay? So I can plug in 0, I can plug in -1, I can plug in -2, and I can plug in -3. So let's get those values by just using our calculator. -0.3 times the square root of 1 minus 3 times 0. Okay? Close the parenthesis after times the 0, and then add 4 after you close the parenthesis for the square root, and you get 3.7. Okay, so now we're going to do it again. Now we plug in -1, and we get 3.4. Now we plug in -2, and we get 3.206. And now we plug in -3, and we get 3.051. Okay, so we're going to graph that. So 1/3, 4, 0, 3.7, -1, 3.4, -2, 3.2, and -3, 3.05. Now this was a starting point, so it starts here, and then it goes to the left and down. So the reason it went to the left is because you've got this -x here. And the reason you're going down is because you're now going to be, from your range, you're now going to have all of your outputs that are less than or equal to 4, okay? Your square root is either going to look like this, okay? This is positive x and a is positive. This is positive x and a is negative. This is negative x and a is positive. And this is a is negative and x is negative, okay? So this graph is now going down and to the left, okay? So when you have a square root that needs to be graphed, you need to make sure that you have 5 points. A square root has a starting point, so get the starting point, get the domain, then plug in points that are in the domain, okay? Plot all the points. And then it goes from starting point and then follow to the other points. And then you can find your range at the end. Okay, number 3. Okay, I'll do this. We'll do that. Okay, f of x equals 1.1 times the cubed root of 3x plus 1 minus 4. So this is a cubed root. So this does not have a start. Okay, we can think of that critical value we want because we want a few points to the right, a few points to the left because we want to see that pretty curve that we have going on with a cubed root. So the first thing is I want my critical value. Okay, so I want to know what makes 3x plus 1 equals 0. Well, that's going to be x equals -1/3. So please do not round your critical value because it should always be the value that makes this 0. If you round this to -0.3, that will not make this 0. Okay, so we want to show what's the value that really makes it 0. So plug this in and we would get 0 here times that minus 4 would just give you -4. Now remember, the domain in the range of all cubed roots is always all reals. Don't forget that. Okay? So that means we don't want this point up here. It's not the start. It's actually the point that would be in the middle of the graph. So we want 2 points that would fall to the left and 2 points that would fall to the right. So what's an x value that's smaller than -1/3? -1. And what's smaller than -1? -2. What's bigger than -1/3? 0. And what's bigger than 0? 1. So now we just plug these points right into our calculator. Okay, 1.1 times the cubed root. If you have a graphing calculator, if you hit math, you can go down to the cubed root option. 1.1 times the cubed root of 3 times negative 2 plus 3. If you don't have a graphing calculator, just have a scientific calculator. Just look for the cubed root button. It looks like this on your calculator. Okay. And then minus 4, and that gives us negative 5.881. And then we're going to plug in negative 1, and we're going to get negative 5.386. And we plug in 0, and 0 is going to give us negative 2.9. And we plug in 1, and that gives us negative 2.254. Okay? So, negative 2, negative 5.81, negative 1, negative 5.386, negative 1/3, negative 4, 0, negative 2.9, and 1, negative 2.25. Okay, and just connect points. There you go. So, if you have a cubed root function, not a square root function, remember, the difference is you don't have a starting point. You have a critical value. You get the point in the middle so that you can make an accurate depiction. If you have this point, okay, when you find points to the right and to the left, you'll be able to make that nice shape that is a cubed root. Now remember, if a was negative, what would happen is this part would be up and this part would be down. But just when you're graphing the cubed root function in detail, get the critical value, okay, keep it exact. So the domain and the range are always all real numbers. And just make sure you have 5 points, 2 that would fall to the left of the critical value and 2 that would fall to the right. So before we end graphing square roots and cubed roots in detail, let's go over 2 variable inequalities. Okay, so if I said to solve each, number 1 was y is greater than the negative square root of x plus 3 plus 2. Now this is a 2 variable square root inequality. The solution has to be, okay, the solution must be graphed. Because the solution to a 2 variable square root inequality is all of the ordered pairs x comma y that make this inequality statement true. And the only way to show that, because it's an infinite area of ordered points, the only way to show that is by graphing. So the first thing, this is like all others that we've done, the first thing we need is our boundary. Our boundary is going to separate our solution from our non-solution. So our boundary is when the left equals the right. So y equals negative square root of x plus 3 plus 2. So that's the first thing we need, okay? We need the boundary. Now, that means we just have to graph a square root in detail. So for a square root, the first thing we need is the starting point. So what makes that equal 0? That's going to be negative 3. So it starts when x is negative 3. And when you plug in negative 3, you'd output 2. So we just need a few more points. Now, can we plug in values that are greater than negative 3 or less than negative 3? Well, let's see. Can we plug in 0? Yes. Can we plug in negative 4? No. So we can plug in values that are greater than negative 3. So I could plug in negative 2, I could plug in negative 1, 0, and 1. So let's do that. Remember, if you have a calculator, you don't have to try and pick points so that you can evaluate this nicely and have an integer value. Just use your calculator. So that's going to give me 1. This is going to give me 0.586. It's going to give me 0.268. going to give me 0. So plot these points. -3, 2, -2, 1, -1, 0.5, 0, 0.2, 1, 0. Now, should the boundary be dashed or should it be solid? Well, is the boundary part of the solution or not part of the solution? The boundary is when the left equals the right. Is the left allowed to equal the right? No, it needs to be greater. That means this should be a dashed boundary. So this was a starting point, so it goes like this. Now, notice, none of this is part of your function. So when you test a point right now, you cannot test anything that would not be in the domain of the square root of x plus 3 here. So all of this area right here, you better not shade any of it, okay? Because all of this area that's to the left here, okay? It's not allowed, those x coordinates are not allowed to be plugged in because you would get the square root of a negative number. So you're either shading everywhere above the boundary, look, the boundary starts here, or everywhere below the boundary. So I can tell 100% if the point 0, 0.26 is on there, then I know for sure that the point 0, 4, 1, 2, 3, 4 is not on there. And notice, it is above the boundary. You do not pick a point over here because if you picked it and you plugged it in, you would not be able to evaluate it because you would get the square root of a negative number. So we have to see, is 4 greater than negative times the square root of 0 plus 3 plus 2? So is 4 greater than, and now put that in your calculator. And we get the value we have there, 0.268. So is 4 greater than 0.268? Yes, it is. So that means everywhere, this is the true side, that means everywhere above the boundary, the infinite space above the boundary is your solution. Do not shade anywhere that's not part of the domain of this boundary, which is everywhere to the left of the starting point. Okay, so that would be the solution to this problem. Now, if you had a cubed root does not have a start. Okay, so if you had to do a cubed root like this, notice it's either shading everywhere above or shading everywhere below. You have no restriction like a square root inequality. Okay, so just be mindful of if you have to solve a 2-variable square root or cubed root, it's just like the previous inequalities, 2-variable inequalities we've been doing, except the boundary, of course, if it's a square root, is going to be a square root. The boundary, if it's a cubed root, is going to be a cubed root graph.